And welcome back to non-IITian. So this is going to be the last lecture on this series of groups, and till now we have discussed all the essential things which we need to discuss about groups. For example, we have discussed a lot of examples of groups, and we have dedicated probably uh, two lectures to talk about the collection of the most important examples of groups, how to count homomorphisms, what are normal subgroups, how to deal with quotient groups, things like that. And more importantly, we have given a lot of exercises intrinsic through the lectures, which are essentially important to induce your conceptual depth. So this is going to be the final lecture, and in this particular lecture our primary goal would be to initially talk about class equations, and then we will be moving on to the discussion of abelian groups in some sense. So let's start. So what we are going to discuss today is, firstly we are going to discuss about class equation and abelian groups. So this will be our main goal, and finally we will attach a few notions of non-abelian groups, but there is typically nothing to discuss very specifically about non-abelian groups, because in most contexts non-abelian groups come out as a as a counter example to certain very important theorems. For example, I'll introduce what is the Cauchy theorem of groups, and you'll see that the Cauchy theorem holds in general. So we'll see that in abelian groups we have a converse for Lagrange's theorem, but in non-abelian groups that is not the case, and the example would come out to be the alternating group of four objects. So typically, let us first discuss the notion of a class equation. So if you recall, then we had previously discussed about the following notion, that the conjugacy class of an element A, so this is defined to be the collection of elements of the form G A G inverse, such that G is in G. And this particular group, this actually came out as as the image of the induced homomorphism of the action by conjugation of a group on itself. And the kernel of that particular action came out to be the centralizer of A. And from there we had induced the fact that in this case, so these are basically the orbits of the action by conjugation. And so and the stabilizer. So I hope I didn't induce this notion, stabilizer of the same action. So let me just give a very brief of it. So recall, we had an action G on G by we can just take it to be any set X. So G on X by G acting on X as simply what we write as Gx. So here we write the orbit of an element X in capital X as the collection of all elements of the form Gx as G traverses over the group G, and Gx, so this is called the stabilizer of X, and this is called the orbit. So in most books you will also find this notation, orbit of X. So this is the collection of all the elements G in G such that X is fixed under G. Okay. And we have something called an orbit stabilizer theorem, which is a very well known theorem in the context of group actions. Orbit stabilizer theorem, which says that if provided the group is finite in some sense, in the general case you will get it to be a bit different, but if G is finite, so if G is finite, then the order of G is the order of orbit of some element times the order of the stabilizer of that element. This is called the orbit stabilizer theorem. And in the context of if you assume that this is infinite, then what at most we can say is that the index of the stabilizer in G, this equals the cardinality of the orbit of X. Okay. And now something which you can easily observe, that if this action is by conjugation, then these orbits are exactly the conjugacy class of the element x, and the stabilizers are all those elements g in G such that G inverse is exactly equal to x. So this is nothing but the conjugacy class of x in G. This is the centralizer of x in G. So from here what you can conclude is that hence the cardinality of G divided by the cardinality of the centralizer of an element is exactly equal to the conjugacy class of that order of the conjugacy class of that element. Okay, fine. Now one more context what you can come up with is the following thing, which you can take as an exercise again, that you can induce a relation on any group G by saying that two elements are related if and only if there exists an element G in G such that A is equal to G inverse. This is called the relation of conjugacy, and what you can prove is that this is actually an equivalence relation. So this is an equivalence relation. Moreover, the conjugacy class, the equivalence class of any element under this relation is actually the conjugacy class of that element. And we know by the definition of equivalence classes that they partition the set on which they are acting. So what we have is the following. So the cardinality of G, again under finite case, we are obviously talking about finite case, otherwise the cardinality in some sense doesn't make a proper sense. So this is the orders of all the conjugacy classes of the elements in G, right? So since they partition G by viewing them as an equivalence class, so they partition G. But from here what we can observe that this is nothing but the cardinality of G divided by the conjugacy class of each elements in G. Okay. But then observe something very interesting, that is, suppose A is an element in the center of G, then what should be the conjugacy class of A? I'm extremely sorry because I'm just confusing out what I was saying. I'm sorry. So the centralizer of A in G. So this is the collection of all the elements G in G such that G inverse is equal to A. But we know that since A is in the center, it commutes with every element of G. So therefore this should be nothing but the whole group G. And therefore the cardinality of G mod the centralizer, cardinality of the centralizer will come out to be 1. And hence this comes out to be 1 plus 1 and so on till 1, and these are number of times the cardinality of the center plus all the elements in G except the center of this particular thing. So this comes out to be, so therefore we have the cardinality of G to be the order of the center of the group plus sum over all the elements which are not in the center of the cardinality of G divided by the cardinality of the centralizer of G, and this is what we call the class equation. This is what we call the class equation. So this is the the structure of the class equation which you will get in any standard book, but at least this works equally well, because the only thing which differs from here is that you are separating out the elements in the center, and that's the only thing you are trying to do. So I hope it's clear, right? Fine. But this actually helps you prove something very interesting, as we'll see now. Okay, so this is a theorem that if G is a group of order p squared where p is a prime, then G is abelian. Okay, then G is abelian. In fact, on a general note, any p group So a P group is a group of prime power order. So any P group has a non-trivial center. Okay, and the proof is as follows. So first let us prove that if G is a P group, then it is a non-trivial center, but the proof actually comes out to be quite interesting from the following sense. See, the order of G is, suppose, P to the power alpha, where alpha is greater than or equal to 1, let's say, and P is a prime, obviously. Now we already know that the centralizers are actually subgroups. So the order of the centralizer of any element in G, this will be of the form P to the power some k, such that k is greater than or equal to 0 and less than or equal to alpha, right? Since this divides the order of G. Now what do we need to show? We need to show that the the center has at least one more element than the identity itself. What do we have? We have the order of G to be the cardinality of the center of G plus sum over all the elements in G over the centralizers of G. And I'm not just not denoting the summation over what elements once more. Okay. Now something interesting which you can observe is that now this particular term, the cardinality of G by this actually comes in the form of P to the power alpha minus k, right? So what do we have from here? So what do I need to show? I need to show that there is at least, identity is already there. So it's actually of the form 1 plus summation cardinality of G over the centralizers of A, where 1 comes from the conjugacy class of the identity element 1 in G. But then observe that if there does not exist an element A in G such that the order of the centralizer of A, this is exactly equal to P to the power alpha, then P to the power alpha minus k, this particular term is always is always divisible by, so it's congruent to 0 mod p, and because alpha minus k will not be 0, so it will be some prime power, okay, is congruent to 0 mod p. And since the order of G is also P to the power alpha, which is congruent to 0 mod p, so we have so if I take this to be 1, then we have 1 mod p, implying that 0 is congruent to 1 plus 0 mod p, which implies 1 is congruent to 0 mod p, which implies p divides 1, which is a contradiction because p was a prime. So therefore there must exist some element in G other than identity, obviously, because we have already assumed identity into our consideration, such that the order of the centralizer of A should be exactly equal to P to the power alpha, but that will necessarily imply that A is an element in this in the center. So there is at least one more element in the center, okay, which implies that the cardinality of the center has to be greater than 1. So it's non-trivial. Now suppose the order of the center is the order of the group is p squared. Now since the center is non-trivial, so it's greater than 1, and it divides the order of G, which is equal to p squared. So what are the only possibilities for it? So just wait a second. Right, so I had to pause the video. I had got a call. Nevertheless, so the center is yeah. So therefore, what are the possibilities for the cardinality of the center? So it's either equal to p or is equal to p square. So what I need to do, I need to show that it's actually the whole group to prove that the group is abelian. And for that, what you can try and do, the obvious way we usually proceed is that we will proceed by contradiction. So suppose there exists an element A in G such that A is not in the center. Okay, then what do we have? So if A is not in the center, then obviously every element of G does not commute with A. So what I can try and do is that I can consider the centralizer of A. Now this is also a subgroup of G, and clearly it will strictly contain the centralizer of A. And see, on general it will obviously strictly contain the center of G, because every element in the center will obviously commute with A by definition of it itself. And the element A itself, it's not in the center, but it's in the centralizer, because every element obviously will commute with itself. So it's properly contained here. And the centralizer is an element of G. Is a subgroup of G. So now, firstly, the order of the center will be strictly less than the order of the centralizer, and the order of the centralizer will divide the order of G. But since we have assumed that the center is not the whole group G, what does that mean? That means that the order of the center can be P. So that means the order of the centralizer must be strictly greater than P and a divisor of the order of G, so it must be exactly equal to P square. But this means that the cardinality of G, the cardinality of the centralizer is exactly the cardinality of G, but being a subgroup, this means that this is exactly equal to G. But that means every element of G will commute with A, so that implies that A is in the center, which is a contradiction to our initial assumption that A is not in the center. And hence we have a contradiction. So thus what was our initial assumption? That there is an element outside the center in the group, which we produced a contradiction. Hence every element of the group must be in the center, and hence it's exactly equal to the center. Okay, but this need not be true in the case of groups of order p cubed. In groups of order p cubed, what you will see that obviously the center will come out to be non-trivial. So the possible orders will be p squared, or p cubed. But once the center has order p squared, it will automatically be p cubed by whatever we did here. So the only possible order of the center for a non-abelian group of order p cubed will come out to be exactly p. Okay. So for example, you can consider the group, for example, let's say D4, which has 8 elements. So these are the symmetries of the regular square. Or you can also consider Q8, the quaternion group. So both of these are non-abelian, and the order is 2 cubed. So since both of these are non-abelian, their centers will have exactly 2 elements in both the cases. Okay, and here the center will come out to be 1 and minus 1, and here the center will come out to be 1 and r squared. Okay, in fact we had previously discussed about this particular thing, that if you have the group Dn where n is even, then the center consists of 1 and r to the power n over 2. And if n is odd, then the center is trivial, it has only one element. Moreover, you can try and prove that the dihedral group is not isomorphic to Q8, though both of them have the same order. And what you can argue is that the subgroup structure of Q8 and the subgroup structure of D4. You can try and do this on your own, because how many elements of order 4 will be there in Q8? You will get I, J and K. You will have 3 elements. How many elements of order 4 will be there in D4? So there will only be 2, one r and r cubed. Yeah, so they cannot be isomorphic. Nevertheless, this was the thing which we actually wanted to discuss in this particular context. Now let us give us some important examples of class equations, and one of the most important examples of class equation is that of the the class equation of dn, and the class equation of dn comes out to be in the following sense. Okay, so it comes out to be 1 plus 1, so 2 elements, and this holds when n is even. Okay, so plus we have 2 elements of conjugacy class having n by 2 elements, and the rest having conjugacy class of 2 elements. So these are n minus 2 by 2 times, and this happens if n is even. And in case of n is odd, I have only one element in the center plus an element which consists of n elements in the conjugacy class, and the rest of the elements having 2 elements only. Okay, so these are n minus 1 by 2 in number. So this is if n is odd. Okay, fine. Yeah, so I hope so. What should be the class equation of an abelian group? All ones, right? The class equation of an abelian group should all be ones. What is the class equation of Q8 probably? So what is the class equation of Q8? So the class equation of Q8 will typically come out to be in the following sense. So it will be 1. So what are the elements in the center? You have 2 1s, and then you have all 2s. Okay. Should I discuss something more? Nevertheless, let's leave it. Let us give a interesting result for the time being. That is, if G is a group of order P times Q, where P and Q are distinct primes, and suppose P does not divide Q minus 1, then G is isomorphic to ZP cross ZQ, which is actually isomorphic to ZPQ. So it's a cyclic group. So you can prove it in some sense that Zm cross Zn. So these are called direct product of groups, and here the group is formed by just component wise inducing the component wise operations. So this is actually isomorphic to Zmn if and only if the GCD of m and n is equal to 1. And this is in some sense a consequence of the Chinese remainder theorem. And if here P divides Q minus 1, then there are 2 possibilities. One possibility is that it can probably be cyclic still, and the other probability is that it will be a non-abelian group. Nevertheless, it's a good time that we talk about the famous Sylow theorems, but I am gonna not get into the proof of these obviously, but I will be just explaining it out. So let G be a group of order P to the power alpha times M, where M is co-prime to P. Okay, that is, alpha is the highest power of P, which divides the order of G. Then we have the following 4 consequences. Number 1, there exists a subgroup H of G such that the order of H is P to the power alpha. Such a subgroup is called the p-Sylow subgroup of G. Okay. Next is that 2 p-Sylow subgroups. This is how we write Sylow subgroups. So 2 p-SSGs are conjugates, and hence if H is a unique p-SSG, if S is a unique p-SSG, then H has to be normal in G. So unique Sylow subgroups will come out to be normal. And number 3, that let NP be equal to the number of p-SSGs. Then we have NP dividing M. So NP will divide the residue of the order of the group, and NP has the form 1 plus k times p. That is basically np is congruent to 1 mod p. Okay. Now the first statement is what we call basically the Sylow existence theorem. The second point is basically what we call the Sylow conjugacy theorem, and the third point actually helps you count, so it's called the Sylow counting theorem. And the third particular statement actually helps you to judge whether a given PSSG exists uniquely or not. Okay, so let us try to analyze whatever I said about the theorem that the order of G is P times Q and P does not divide Q minus 1, then G is cyclic. Let us try to prove this out. Okay, so I hope you remember, and if you don't remember, then you can just argue from here. And the fact that H and K are subgroups of G, then HK is also a subgroup of G if and only if H is in the normalizer of K, or K is in the so it's contained in, so K is in the normalizer of H. That is, one of them normalizes the other. So if one of them is a normal subgroup, then you are done. Okay. If one of them is a normal subgroup, then it will obviously be a subgroup of G. So let's try and prove this out. So proof. See, observe that by whatever we said, since P and Q are distinct primes obviously, then what do I have? So firstly, NQ must be of the form 1 plus K times Q. Will it work? Yeah, I hope it works. So NQ is equal to, no, let us first write it properly. Wait a second. Yeah, so what I was trying to say is the following. So by Sylow theorems, there exists a group P of order P and a group Q of order Q. Okay, sorry, of order Q. So these are the corresponding PSSGs and the QSSGs. So firstly, observe that Q does not divide P minus 1. So P does not divide Q minus 1. Now, what are the number of Sylow P subgroups? So it should be of the form 1 plus K times P. And what are the number of elements? What are the number of QSSGs? So it should be 1 plus K times Q. And we know that NQ, we know that NP must divide Q. What does that mean? That means that 1 plus K times P must divide Q, right? So, and from here what do we conclude? That 1 plus K times Q must divide P, right? But see, this typically means that Q is of the form 1 plus K times P times some U. Am I doing it correct? Yeah, fine. Okay. And what does that mean? This means that P is of the form. Do I need to get into this sort of a details to prove it? I think not. See, I actually construct out these proofs on my own, so therefore, I often get confused while lecturing and giving the proof, at the same time. Okay, so I think I have got an idea. So now, what are the only divisors of Q? Since Q is prime, 1 plus Kp can either be 1 or 1 plus Kp can be equal to Q, right? But 1 plus Kp is equal to 1. This would mean Np is equal to 1, which implies that P is normal in G, right? Because it comes out to be a unique PSSG. Otherwise, what will happen? So otherwise, what do we have here? So then modulo P, I get Q is congruent to 1 mod P, which is a contradiction because we have given that P does not divide Q minus 1. So therefore, the PSSG is clearly normal in G. Therefore, P times Q form a subgroup of G, because P is normal in G, so P times Q will form a subgroup of G. And what is the order of P times Q? So it is exactly equal to PQ, which implies P times Q is equal to G. But PQ, this is actually what we call an internal direct product. Internal direct product. We did not get into that, but you can just take it as a fact. So this implies that G is actually isomorphic to ZP cross ZQ, because after all, the order of P is a prime P, so therefore it is isomorphic to ZP, and the order of Q is a prime Q, so it's isomorphic to ZQ. And this is what we require to prove. Getting stuck while proving things is actually quite interesting. So I hope you got it. And this is the way you usually work out things. Okay. Fine. Now let us finally get into the notions of abelian groups, and here I won't be getting into much of a details, but let us just give a brief thing about what are abelian groups. So before that, let me produce the theorem of Cauchy, which is quite a very, very important theorem. So theorem of Cauchy. And the theorem of Cauchy says this typical thing, that let G be a group and let P be a prime such that P divides the order of G. Then there exists an element in G of order P. And the proof of this particular thing is not big, and in fact it's actually easy, but it involves, at least the proof I typically remember, it actually involves working out with with quotient groups. Okay. What more can we talk about? So this is a very important theorem, is that if G is a finite abelian group and D divides the order of G, then G has a subgroup of order D. And this is the famous converge to Lagrange's theorem. But this does not hold in general, because so in A4, what is the order of A4? So the order of A4 is 4 factorial upon 2, which is 12, and 6 divides the order of A4, but there does not exist a subgroup of order 6 in A4. Okay. Okay, so something very interesting which I should write here. So it's a very important observation, which is that if G is a group and H is a subgroup of G such that the index of H is 2, then H has to be normal in G. And you can take the proof as an exercise, but the proof basically follows from the typical fact that if I consider G mod H to be just representing the collection of left cosets, then it will only contain elements of the form H and GH. So these are the left cosets, and what are the right cosets? R. So this should be of the form H times some HX. But obviously observe that since we have only two equivalence classes, and G is not in the equivalence class of H, and X is also not in the equivalence class of H, and since we have only two possibilities, so G and X must be in the same equivalence class. So this must exactly be equal to HG as well. And then you can easily observe that G of H cannot be equal to H, because after all, what we have from here is that G is H disjoint union GH, and is also equal to H disjoint union HG by the properties of equivalence classes. But from here you can observe that G of H must be equal to H of G. You can just cancel out H from both sides from a set theoretic notion. So I hope it's clear. And the final thing which we are going to discuss here is the following, which is the fundamental theorem of finite abelian groups. And this says the following, that every finite abelian group G is isomorphic to a direct product of cyclic groups of prime power order. That is, G is isomorphic to groups of the form, say, P1 to the power R1 cross P2 to the power R2, so on and so forth till Pk to the power Rk, that each of these Pi's are primes. And the important takeaway from here is the following, that is, so you can take this as a corollary, the number of non-isomorphic abelian groups of order n is equal to P1 to the power A1 times P2 to the power A2, so on and so forth till Pk to the power Ak is equal to P times A1 times P times A2, so on and so forth till P times Ak, where P of Ai is equal to the number of partitions of Ai. And this readily follows from the fact that this cyclic decomposition actually, here R1, the total order should be exactly equal to G. So this actually corresponds to what are the number of ways in which you can actually separate out each of these exponents of the prime powers. Okay. And this is a very interesting theorem because you often get questions from here, that what are the number of non-isomorphic abelian groups of order, let's say 8, of order let's say 6, so on and so forth. Fine. Okay, so we have discussed a lot, and one final thing which you can try and do, so as an exercise, prove that phi from G to G by phi of G is equal to G squared is a homomorphism if and only if G is abelian. Okay, I hope it's clear. Fine, so that's all for this lecture, and this is going to be the last theoretical lecture on groups. I hope you have done all the exercises which I've given throughout the lectures. So from the next lecture onward, we will dive into some problem solving sessions. I will take up about 3 problem solving sessions where we will be discussing about very important and very conceptual problems in details from the context of IIT JAM, and probably some higher competitive exams as well. Nevertheless, meet you guys in the next lecture.